those look like.
Yeah.
And then I'll send you.
You just need the link for it. I'll just do that right now.
Okay, sweet. Yeah.
Yeah.
I mean, it's a couple. I don't know how much there's overlap, but I wanted to propose muscle-based TRPO.
So if you have, especially if you have some information for the students about where they can get an XML file for it.
There is one possibility, but
yeah, because we don't really cover how to use Mujoku really, but I think that something like that would be great actually. You've seen Van de Pen and Jason's paper in the ICLR submission, right? Muscles versus PD versus torques.
I haven't seen the LCLR one. I've seen him, he came by and gave a talk at OpenAI, on those comparisons. But yeah, I haven't seen the final one.
The one where it basically concludes that PD control is the way to go. All right, I should probably introduce you. All right, guys, so we're going to get started. It's my pleasure today to introduce Igor from OpenAI. So Igor is a research scientist at OpenAI who he did his PhD at the University of Washington with Emmanuel Todorov and Zoran Popovic, where he worked, well, initially on some really cool things in character animation, having characters execute really complex behaviors, really complex in-hand manipulation with arms, and some really interesting stuff with simulated muscle models. Igor then moved on to working in robotics, when he did a postdoc actually here with us at UC Berkeley with some humanoid robots. And now he's at OpenAI doing, I guess, all sorts of exciting things. So, yeah.
Yeah, cool. Thanks for the introduction, Sergey. So everybody can hear me all right, I guess? Yeah, OK, cool, great. So I'll talk today about some of the things that Sergey has already covered in previous lectures, but kind of give you a slightly different take on it and mostly focus on direct collocation methods. So from the first couple of weeks before, we were talking about learning dynamics models, doing how you can do optimal control with learned or known dynamics models, and how you can learn policies in that case, say, by imitating optimal controllers. And what those lectures mostly focused on was using forward dynamics models, and mostly using shooting methods, such as, for example, LQR or iterative LQR, or differential dynamic programming. And today, I'm mostly going to cover same goals, but we're going to look at inverse dynamics models and direct collocation method in more detail. Then we'll be able to see how you can optimize complex movement involving contacts with these direct collocation methods and applying some of the ideas in general that we've learned from looking at them. Also, how you can deal with unknown and uncertain dynamics, and some of the applications, say, to biomechanics. So let's get into it. First, we'll talk about trajectory optimization with direct collocation. And to give a little bit of a review, because I think it's been, say, a couple of weeks since you last covered it, how would you use trajectory optimization to create movement? Let's say you have some system that starts in some initial state, x0, and you want to get to have it get to the target state. We've already seen forward shooting method as a way to find a solution where you optimize for the sequence of controls. And then you have a forward dynamics function, and then you apply the controls, and you get a sequence of states as a result. And then you can look at, find the controls that minimize some cost function, like, let's say, getting to the goal. And as we've seen before, this forward shooting method has problems with conditioning, has poor conditioning, where by changing the initial state, by changing the initial controls only slightly, you have very different changes in the resulting state trajectory. And kind of you got the intuition for it last time when you saw this equation unrolled, where basically any particular state ends up depending on all of the controls that came before it. So that's why basically U1 where is it? Ends up influencing like all of these resulting states. Another issue that kind of wasn't discussed too much, but is still very important, is that you have a very narrow feasible region with forward shooting methods. So because this dynamics function, you can think of it as an implicit hard constraint on the space of trajectories that you can have. So if this 2D sheet is the space of all the possible trajectories, making sure that the trajectories obey the dynamics function only narrows you down to a particular feasible region in the space of trajectories. And it's a hard constraint because you can only get trajectories as a result of rolling out forward dynamics. So for example, if you start with some initial guess, and this is the optimum, you have to make a lot of steps during your optimization that seem like very roundabout to get to the optimum. And you may not actually, you may get lucky and that may happen during the optimization progress, or you may not, and you may just get stuck here and be in a local minima and not escape it. On the other hand, if, for example, this dynamics were to be a soft constraint, and this, rather than being a 0 or 1 region, instead was something like the energy and like how likely you are to be in a particular, how likely you are to have a particular trajectory, well, you could potentially see that during the course of the optimization, you might be able to jump over intermediately through the space of unfeasible, implausible trajectories and get to the optimum. So, I may have intermediately in the optimization some motions that say fly towards the goal and totally break the laws of physics. And you're free to entertain that possibility during the optimization. But in the end, you would still settle onto a physically plausible motion. And I'll get back to this. I'll make this clear and have more examples later on. One thing that I should also add is that this is not some weird pathological case. This does come up in practice often, this issue with that you have to stay on the space of physically plausible movements. So, for example, collisions often have problems where I'm trying to, I have my hand here and I want to move it over here, and if you might try to have a motion that moves this way, but you can never have the hands penetrate or cross each other, and you might kind of get stuck in this minimum. Whereas if you're able to break the laws of physics for a little bit, you might have the hands collide through each other at first early on in the optimization, but then find a solution that doesn't have collisions later on. Or similarly, another way that this can come up in practice is if you're trying to optimize trajectories for humanoid motion, the initial guess would have the character, say, falling down a lot. And if you always have to satisfy physics, you may never just get out of that minimum. So it makes the solutions also, it makes forward shooting methods pretty sensitive to the initial guess. And so there's some things that you can do to mitigate that. So for example, initializing from demonstrations, or for example, for avoiding collisions, you may use some other method to find a collision-free path and then use that to initialize your trajectory optimization. Or you can have some randomization. So for example, I don't know if Sergey already talked about path integral control or if you will, but basically kind of incorporating more of the elements of random search also can help. But it's sort of orthogonal to trajectory optimization. So from the last lecture, as opposed to shooting methods, you saw collocation methods, where instead of optimizing for the controls, you simultaneously optimize for the controls and states. But you still involved the forward dynamics function here, where the controls were constrained to be such that the previous states and controls leads to the next state, which are now the optimization variables. We're going to take a slightly different view here and only optimize for the states. And the controls, which were optimization variables before, will now be implicit functions of the state. And you'll be able to recover the controls from the states using an inverse dynamics function. And this is the direct collocation method and the basis of it. Yeah?
Is F always invertible? You could imagine you could have like more inputs than
yes, yeah. And in general, it may not be. We're going to look at the cases where it sort of is. So where you find, say, a least squares solution to, or like something that has the notion of like a least squares solution to F, or you've defined enough kind of prior information that you always have a unique solution. But yeah, we're going to look at what these inverse dynamics functions are. So one nice thing about this formulation is that now you have the states being largely independent of each other. So the control only depends on the two nearby states, and it doesn't depend, say, on the previous controls down the line. So you don't have the conditioning problems that you saw before with shooting methods. So changing, for example, your optimization variable, like changing x1, has a similar effect to changing, say, xt. Whereas before, like changing x0 had a very different effect from changing like ut. Another kind of nice side benefit is that you don't have the instabilities that are associated with forward integration, because this is not a forward dynamics function anymore, but I think I'll get into that a little bit later. Right now, it's kind of a subtle point. But the big advantage is that now this inverse, the satisfaction of dynamics is an explicit rather than an implicit constraint on your space of trajectories. And it can be a hard constraint, but it can also be made a soft constraint. So you can have kind of a feasible region that is more like this energy function. And you could be less prone to local minimize, we'll see later. So kind of just to compare and go over it again. So forward shooting methods, you optimize over the controls, and the sequence of states is going to be an implicit function of those. And the dynamics, you can think of it as being always implicitly satisfied. With direct collocation, you optimize over the states, and the controls and other quantities, such as, say, constraint forces like contact forces, are implicit and are a function of states. And the dynamics is now an explicit constraint that can be made soft if you want it to be. Yeah?
So if optimizing over just the states is considered direct collocation, what do you call it when you're optimizing over the states and the controls?
So there's different kind of nomenclature for this. I think that also tends to get called the collocation method as well. But I think, like in general, depending on the literature, like people tend to just like lump them all as collocation methods. And there's two different like variants of this, like where it's like states and controls or just states. There isn't, at least like I haven't seen, I don't know, maybe you have a better suggestion, but I haven't seen like that, like having a specific terminology for each of these two approaches.
Which is more common in practice?
It depends. So these collocation methods also get used, for example, in other fields, like let's say fluid simulation, where you can like simulate fluids, and there are no controls. You just have the states, and there you're optimizing just for the states. So that's very common in like computational or like fluid dynamics. These collocation methods in general are probably less widely used, especially like in, say, DeepRL or like this setting. But I'd say both. I've seen both of them kind of get used about the same frequency. But again, it depends on the field. So let's look at this. Does that answer your question? Okay. So let's look at the inverse dynamics model in more detail. Basically, again, what it does is it describes what controls and forces or other quantities you apply when you transition from xt to xt plus 1. So one way you can possibly get this model is to learn it from data. you try to run your, let's say, run your robot under some sequence of controls. So get a sequence of states, get a sequence of controls. Take the training data input as being like xt and xt plus 1. Take your favorite function approximator, like let's say a neural network, and make it recreate targets U. And yeah.
But that might not really be useful for setting like the set where these minus 1 xt plus 1 may lay, right? Because like the neural network will always tell you an output, even if it has never seen this pair. But your interest, like sometimes a transition will just not be possible. So like the answer should be no, there's no U, but like.
Yeah. And so there's various other things that you have to do here. Like, let's say, implicitly define that if I haven't seen a particular training case, then that's not going to be a feasible case, or things like that. So it's, there is subtle kind of issues with that. And I can point you to later, so Jan Peters and his lab has done some work on learning inverse dynamics models from data. And yeah, there's some extra special things that you have to be careful of. But I mean, in general, people were able to learn these models from data. We are going to see, though, if you have rigid multi-body dynamics, like let's say you have with robots, we can do better when we know the system parameters. So kind of to give you a brief intro to rigid multi-body dynamics, let's say you start with your state being the generalized coordinates or all the degrees of freedom of your system. So for example, like all the joint angles of the character, and if the character has a free-floating base, let's say all the angles and the world position of the character and the world position of your system. And from the neighboring states, you can calculate the velocities and accelerations of how these degrees of freedom, and like how they're changing throughout time. And these resulting generalized coordinates have to obey a particular dynamics equation. So this may look complicated, but this is basically kind of, you can think of it as a generalization of f equals ma at any point in time that needs to be satisfied, where you have a generalization of M, like some particular mass and inertia matrix, and some Coriolis terms that come out, and where you have the controls and the control actuation matrix. So U are your controls, but you may actually have more degrees of freedom in your system than you have controls. For example, like the free-floating degrees of freedom, you cannot really control them. You don't have motors that control where your robot floats in space. And so this actuation matrix B will reflect that, where you're going to say have a diagonal for all, like ones for entries for all the degrees of freedom you can control, and zeros for the degrees of freedom that you cannot control. And you're also going to have, on the other side of the equation, the constraint forces and the constraint Jacobian. So these Fs can be, for example, say three-dimensional contact forces that are being applied on your character, like let's say when it has the palm or the feet on the floor. And this Jacobian transpose matrix will map these this collection, the set of three-dimensional quantities, to your generalized forces that are the dimensionality of X. And again, there's I've gone through it super high level. If that's something that interests you, I would suggest looking at chapters 2 and 3 in the Springer Handbook of Robotics. It has like a really great explanation, a really great intuition for all of these quantities, and actually has like how you derive them. And similarly, Analytical Dynamics: A New Approach is also like, these are two great references. For now, I would just say that a lot of physics simulation packages like MuJoCo provide you with these quantities, so you don't necessarily need to implement this stuff yourself. So that was the dynamics equation, but how does it relate to the inverse dynamics function? Well, the inverse dynamics function, which now, I guess I've abused the notation a little bit before to make it more consistent, but it really is a function, say, of some neighboring set of states. In this case, you can think of it as 3 neighboring states, like xt minus 1, xt, and xt plus 1. And what this function is going to be, it's going to be, you're going to try to find the best controls and the best contact forces that make this dynamics equation hold. And this can be solved numerically. For example, with various approximations, you can pose this, you can make this to be a quadratic program, or you can actually find analytical solutions to this minimization. And Emo Todorov has a good paper for this that is listed in the references later that goes into the detail of this. But basically, what you end up having is like, it's a little bit computationally expensive where, or seems like it, that in order to evaluate the inverse dynamics even once, you need to run kind of an inner optimization problem inside your trajectory optimization. Another thing that you get as a result is actually the minimum of this function ends up being a residual that's going to be very useful later. So it may not be the case that this dynamics equation can be satisfied for arbitrary q's, because you might have a case where the character is just floating above the ground, no forces are being applied, the poses are the character just is in the air, but there's gravity acting on it. So there is going to be some residual in, like, the two sides are not going to match up, and it's going to show up which would basically, this would tell you like how physically plausible is this triple of states. So just to kind of make this concrete, because I guess things were abstract before, here we can go through a simple example for a particle where the dynamics equation is, like, we've simplified these things enough to where it's just F equals ma, and the forces that are acting on the particle is going to be some free force that you can apply, that you can control, and you're going to have, like, let's say, the effect of some gravitational field. And the inverse dynamics function for this simple case, you can just solve for it analytically, and it's unique, where you can finite difference the states to get the state positions to get the acceleration, and you can solve for what the controls should be. And the cost is just like to have the particle stand still throughout the entirety of time. And you have some known initial state in which the particle starts. You have some known system parameters, like let's say the mass of it, and you know the external forces. None of this, of course, is going to hold in the real world, but you have to estimate these parameters, and you have to somehow be able to sense the forces. And now what you're going to be solving for, again in this direct method, is the sequence of states now x1 to xt. And the solution is you would be able to solve, like, satisfy this cost exactly, where you can just basically look at this problem and intuitively tell that the solution is going to be, the states are just going to be at 0, and implicitly the controls are going to be just g, which is going to be basically I'm free to apply the controls that totally negate the gravitational field that is externally being applied to me. So that's kind of to give you rundown, like, how you would end up solving the direct collocation, like what are the unknowns and what are the quantities involved. But in many cases we can't just intuitively guess at what the solution would be. We need to actually solve these resulting optimization problems somehow. And so what's the first thing that you can think of? Well, Chelsea gave a tutorial on TensorFlow on Friday. Why not just take this graph, set up a similar TensorFlow graph, and optimize the resulting problem with gradient descent? And that's actually not a terribly bad idea. The convergence in practice, even for simple problems we've observed, is really slow. Yeah?
So the unconstrained optimization that you have in mind here is one where you have the objective and then these the squared
yes.
error.
Yes, yes, yes.
Are there particular conditions on the coefficient on that constraint that you need, or like do you have any intuition for how to choose that?
So something that you can do and something that I can talk about a little bit later is that you can use something like basically take the idea of continuation methods where you might have a very, very small weight on this dynamics. This dynamics residual is going to be part of the cost. And you may have very small weight on it, and then later on you increase it as the optimization progresses. But we saw that for shooting methods, we have second-order approaches that tend to work a lot better in practice than gradient descent. So we've looked at LQR, and in particular iterative LQR. We've looked at DDP, which LQR is kind of an approximation to the second-order method, and DDP is, you can think of it as the true second-order method for solving forward shooting problems. Similarly, for direct collocation, we can apply second-order methods and, in practice, a truncated approximation to them. In particular, the Gauss-Newton method. So let's say we have the total trajectory. Where is it? Let's say your x is your total trajectory, and you have some total trajectory cost that is this phi is all the features of the problem that you would care about. So it includes that dynamics, inverse dynamics residual, any other cost features. So for example, if you want like the location of an arm, if you want, or the location of the hand, if you want a hand to go to a particular location, kind of phi encapsulates all of these features, and you have a cost on these phi's. So C is a scalar variable that takes an input, some vector of features, and phi is this n-dimensional vector of features. And you can derive its gradient. With respect to the entire trajectory, you just apply the chain rule. And you can also get the Hessian of this trajectory. And what the structure of the Hessian ends up looking like. So for the gradient, you only needed the Jacobians of phi. So basically, the Jacobian of, say, the derivative of how your dynamics residual is going to change with respect to your cost. And also how your scale, with respect to your trajectory. And also how the cost function is going to change with respect to your features. Similarly, in the Hessian, now you need the second order terms. And the Hessian of the costs with respect to the features is usually pretty doable to get, because these costs are usually analytical functions that you define yourself. So it may be, say, a quadratic, and the Hessian of, like, you want the arm, the hands to be at a particular location. That's like a quadratic between your actual hand location and the target. And the Hessian of the quadratic is very easy. But the Hessian of these features is potentially very difficult, because as you saw in LQR, what the approximation was is that you were using first-order derivatives, or first derivatives of the dynamics, and first and second-order derivatives of your cost. And here, with this Gauss-Newton method, you end up using, like, playing the same trick, where you end up using the first and second-order derivatives of your cost, but the second derivative of your features, you're just going to drop it. And this is going to become the approximation to your Hessian. And then you can find the solution by a succession of iterative steps where you basically end up taking, like, assuming that this is a Hessian matrix, and end up taking a Newton step. And I think Sergey covered that before. In practice, you would usually, this Hessian can potentially be, you may not be able to numerically solve this equation, or the Hessian might be singular, so you end up, in practice, adding some damping, so like some weighted identity to it, kind of have the similar intuition that trust region methods have, where at any single iteration of your algorithm, you don't want to make the change in your parameters to be too large. So this kind of acts as a step size. But the problem is, does it require inverting, in order to do this Newton step, does it require inverting this x by t by x by t Hessian at every iteration of your algorithm? Yes, but the nice thing about it is that this Hessian is actually very sparse, because, again, as you saw from the dependency chain, this really should be phi, like any particular features at any particular time only depend on, say, 3 neighboring states. So in the Hessian, for any particular feature, you only have small block, like small region of dependencies here. And there is a lot of methods that can solve this resulting sparse linear system. So for example, for Python, linalg spsolve does a great job with this kind of algorithms. Other methods are potentially possible. So there is more clever, like if you've ever taken numerical PDEs class, or just numerical solutions to differential equations. They've discussed, say, multigrid methods or projection methods or spectral methods. You can play all of these tricks here as well. And in fact, that's kind of an area that's not been explored very much for direct collocation methods, especially for trajectory optimization. And so that presents like a lot of fruitful opportunities here. And again, the constraints that we saw, they could be solved, but you also can, if you wanted to use constrained optimization methods like sequential quadratic programming, to also solve these problems. Any questions so far? So that's kind of the standard solutions for direct collocation. Well, what about when you have dynamics with contact? In the cases of, say, free-flying or driving or swimming robots, or finding collision-free paths for robots, in general, both shooting and collocation methods can be applied. But when you're dealing, say, with legged robots or manipulation, it's pretty difficult, or any situations where you have contact with the environment, it's pretty tricky to apply either method kind of straight up. One of the problems is that you may have discontinuous jumps in the contact forces and also the number of contact forces. So, for example, where is it? You have 2 poses here, and in pose space, they're actually very similar to each other. But one of them has like a hand touching the table, and the other one doesn't. Well, even though they're very similar in the pose space, the set of forces, like this F and the Jacobian of F, actually have different dimensionalities in each of these. Because, say, you're doing a collision detector or collision checking, and you have different you have different sets of forces here. And another issue that you have is that you don't actually have any gradient information for inactive contacts. Let's say the character is sort of hovering a little bit above the ground, and it needs to be standing on the floor. But the optimization actually doesn't realize that it can't anticipate that you would be able to apply forces a little bit later once you start touching the ground. So it's sort of similar to vanishing gradients, where you don't really have gradient flow, but for slightly different reasons. So in general, the issue is that contact activity is an indirect function of state, much like, say, the states were an indirect, like in shooting methods, the states were an indirect function of the controls. But what if we make contact activity similar to collocation methods, or similar to that philosophy? What if we make contact activity a direct optimization variable, like we did for the states? And so that brings us to, say, contact invariant optimization, which is some of the work that we were doing, where you start with a direct collocation method, and as before, your x, your state, contains all the joint angles of your character and all the degrees of freedom. But in addition, the state also contains these contact decision variables, these scalar variables, that basically indicate whether or not a foot or a hand is in contact with the ground at a particular point in time. So for example, you have for the right foot at time 0, you have a contact variable saying 1. Whereas at time t, say for the right arm in this pose, the contact activity variable is 0. But they're independent of your poses, or at least like you're free to decide on these independently of the poses. And again, they're unknowns that you're deciding over. Because they're independent, you do need to enforce a consistency between your poses and C's. And also you need to enforce, as we needed to before, we needed to make sure that the paths are physically plausible. So the consistency for contact, it's pretty simple. Basically, you can say that when the contact variable is 1 for a particular limb, for a particular body part, like the palm of the hand or the sole of the foot, it needs to be touching the ground, and it needs to be not sliding. And you can formulate this equation pretty easily. And when the contact variable is 0, then that particular palm of the hand or the foot is unconstrained, and it's free to move wherever it wants to in space. And the dynamics consistency is similar to what we've seen before. You can use your inverse dynamics function. But now we're making it that all of the forces are active, so that your set of contacts doesn't change. It's always maximal at every time. But we're going to add penalties that basically penalize the use of forces for the body parts where the contact variable is 0. So you're free to, so again, it's kind of a softening of the constraints and making the constraints explicit, where you can always apply forces, like I can push off the air, but if I'm deciding that that variable needs to be 0, I'm actually not going to try to use that force. And so another way of thinking about it is that the trajectory optimization kind of guides the inverse dynamics solver through these contact variables. So there is the interaction between the two optimizations. And now the resulting problem doesn't actually have any discontinuities due to contact, and you always have a gradient as to what actuation you can apply. And again, we can solve it with standard optimization methods like the Gauss-Newton, and it takes about 2 to 10 minutes for a particular motion. So to give you some intuition for how the optimization progresses, let's say you have a character that's, say, lying in a particular initial pose, and it wants to be standing over the target. Well, again, in the early stages of optimization, you can play this trick where you make the physics and these contact constraints be very, very soft. And so you're just getting a motion of a character essentially flying towards the goal. But it already kind of gets into the general ballpark of what the motion should be like. Then you start enforcing this additional constraint that active contacts need to be touching the ground and not be sliding. And what you're going to get is some contact variables, which are actually shown as squares here. They either end up disappearing or they end up going towards the ground. And in the final stages, you say that, yeah, the active contacts should not be sliding. So you end up seeing is that contacts that do continue to be active, they end up converging just to a single point. And other contacts that don't, they become inactive. And in the end, you're going to get, say, a motion of the character where all the forces are plausible and the poses agree. All the forces are plausible and all the contacts agree with the poses. Did anybody have a question there that I saw? Or no? And so what's the idea here? Again, the trick is not necessarily the development of new optimization methods, but a reformulation of the problem, where you start with a minimal representation and you add these auxiliary variables, like the contact decisions, that in general lead to a larger optimization problems, but it's easier to explore search space and it's better behaved. And you need to softly enforce this additional consistency. between all your variables. And this is an idea that we'll go back to later. I think this, in general, that's going to be an interesting recurring theme. So some of the other things that you can do here with this method is it's pretty flexible for generating movements. Let's say you always have the same goal where you need to be standing over the white crosshair, but now you're changing the environment. And depending on the environment, you get different strategies kind of coming out of the optimization, where if the gap was very, very small, you can just like climb over it or step over it. And in some cases, you need to mantle over it. And in some cases, in this case, we also allowed the contact forces to be able to pull on the ground, and kind of got this climbing movement. Or you can basically change the goal and reverse the angle of the torso at the desired angle of the torso at the final location, and kind of get these kinds of preparatory movements for handstands. Or you can set up various goals, like let's say that a hand needs to be at a particular location with a particular velocity. Also, not necessarily humanoid characters. You can have quadrupeds, and kind of how this walking sofa-like creature would climb over a ledge. You can also have interaction with props, where you have additional contact variables between the palms of the hand and the props. And the only goal here is that the prop needs to go to a particular location. And you don't actually say anything about the movement of the character, which kind of emerges on its own. And I should say, so the simplification that you're making here is that characters can have contact only at particular locations. So you explicitly define, oh, there's going to be a contact variable for like between the ground and the foot, or between the hands and the prop. And those are always active. So it's basically, you can't necessarily have like be able to support very large number of contacts here.
So you mean you define the superset of all possible contacts?
Yes.
You can still turn off some of them.
Yes, yeah. The superset needs to be defined. And you can have kind of this interesting multi-agent cooperation as well, where the goal here is to get this character to a particular height. You can also use it for hand manipulation, and similarly have contact variables for interaction between the fingers and the object. And now the goal is for the object to get to a particular location, let's say at a particular angle. And so you can have kind of be able to generate these picking up movements, or various in-hand manipulation. Like let's say here you're defining just the angular velocity of the object, and you're kind of getting these sorts of twiddling motions. And the issue with direct collocation methods actually kind of shows up here, where the constraints are soft constraints, like let's say on the dynamics, on the dynamical plausibility. And so they may not actually be satisfied exactly. You might always have like a little bit of a residual. You may have always a little bit of penetration or a little bit of unphysicality in your movements. But it's still a sensible sketch of what should be happening. You can also do things like pick up the object. You can have multiple hands kind of cooperating to pick up the object as well. So it's a pretty flexible way to generate movements. And again, that's from very simple initializations. You don't necessarily need to have any clever initialize your solution with any clever ways. So, but as we've seen, as Sergey talked about, trajectory optimization only finds a solution to a particular situation, to a particular, like I start in a particular state and I need to get to a particular location. It doesn't actually tell you what to do in every situation. And so that's why we'd like to be learning control policies so that we can interact, or our characters or our robots can act in arbitrary situations. And so I think this should be pretty fresh, because Sergey talked about it just last Wednesday, I guess, by learning control policies, posing that as imitation of optimal control. And we're going to have kind of the same approach here, but we're going to see how kind of direct collocation methods come into play with a similar approach. And so let's say you have the same problem as before, where your system starts out in some initial state and needs to get to a location. Well, you can use kind of forward policy gradient, or like use back propagation through time, I guess Sergey called it on Wednesday. Kind of the equivalent of forward shooting, where you have some policy parameters and you just roll out your sequence of states according to your policy parameterized by theta. And you gauge how well these policies do by the cost function. And again, you have the same poor conditioning problems, where small changes now to your policy parameters can lead to very large changes in your states. So something to mitigate this is, what if you had demonstrations of good movements that already achieve the task? Well, then it just becomes a supervised learning problem for the policies. If you have some expert demonstrations, expert sequence of states and controls, you can just apply regression to, or like use neural networks or sort of supervised learning to match the two. Demonstrations can either come from humans, but the interesting case we're looking at with no supervision is that they can come from trajectory optimization, like we saw on Wednesday. And so how could you do something like that? Well, one way you could possibly do it is you can set up a collection of tasks and find solutions for each of these tasks. So let's say like task 1 would be, say, to move forward 2 meters. And like task n might be move backward 1 meter. You're going to run trajectory optimization problem for each of these possible tasks. Collect all the state and action pairs from these resulting optimal trajectories, and again, train, say, your neural network to map between the two, and hopefully find policy parameters that generalize to in-between problems, like moving backward 0.5 meters instead. And that's not necessarily a totally crazy idea. But some of the issues that come up with this is that this set of trajectories can be very difficult to learn, or it may not even be consistent. So one potential issue is that you can see here the two trajectories where the goal is, like, let's say I have a bird that's trying to stay up in the air, and trajectories for different types of like flappings of the bird. And so one of these is very regular, which is like kind of the bird flapping like this. And the other one is a very chaotic solution where the bird just kind of like flaps randomly. And it's able to stay up in the air, but if this was the trajectory that you're trying to learn from, there's very little structure here. So this one would be much harder to learn than this very regular cyclic trajectory. Another issue is that things can even be inconsistent. So let's say I'm starting from standing still, and I need to start walking with a particular speed. Well, I can start walking with the left foot, or I can start walking with the right foot. And both of these are equally plausible. And depending on kind of random initialization, some trajectories might start walking with the left, some might start walking with the right. But let's say you have a single like a unimodal policy that for any particular state has two conflicting actions, and it would, if it's a unimodal policy, it'll try to do something in between, and that is not necessarily going to be a sensible action to take. I think like policies that are, say, provide a distribution or multimodal distributions over actions could potentially solve this problem, and that could potentially be a viable option. But if you have unimodal policies, as we did before, this could be a problem. So what can we do? And similarly to what Sergey mentioned in the last lecture, we can make it so that, I mean, I think of it as making sure that the policies that we're learning so far feed back into the trajectory optimization problems that we're solving. So one way to think about it is it's as if you're jointly optimizing your policy parameters and all of your set of trajectories with a cost function where your cost is just the traditional trajectory optimization cost that we saw before, but it's going to be the second term that's going to couple the policy and the trajectories together. And we can take a closer look at it. Let's say you have, along your trajectories, you have some controls. And you're going to be training the neural network to try to reconstruct those controls. But it may not be able to reconstruct them perfectly. It may give you an answer that's a control that's slightly different. And so what this term says is what you can do is you can try to adjust the policy parameters, like let's say train your neural network for longer or so to kind of make pi of x match u. But another alternative that you have here is inside your trajectory optimization, you can make u to come closer towards what the policy is guessing. So you have kind of two ways of making this go to 0. And it's a similar idea that we've had in contact invariant optimization, where you essentially add auxiliary variables. Did it die? Oh, no. Strictly speaking, because the only thing that you need is these policy parameters. You can get this set of trajectories can be implicit. But now we're making them explicit unknown variables. And we're going to enforce soft consistency between all the variables we have, which is basically this consistency term. And this results in a larger, now much larger, search space because we have all these trajectories. But it could be easier to explore. So a couple of kind of practical things that come up is we try to run this optimization problem, but we end up seeing that the policy is still not converging. You can kind of see the plot of all the different trajectories. So what went wrong here? An issue that can come up is that the policy learning problem that we're trying to solve is actually pretty different from traditional supervised learning, where at test time, you have errors that are independent. So for example, in recognition, you may, say, propose a label, or your system might propose a label. You might misclassify it. Well, you just mark down your total score, and you move on to the next test image. But in our setting at test time, our policy is going to be predicting a particular action. And it may not get it exactly right. There might be small residual. And it might end up in a state that it actually is slightly different from where it expects to be. And it may make an even bigger error next time. And over time, it may very quickly drift away. So to overcome this, we need to make sure that the policy is also outputting sensible controls for an entire neighborhood of states rather than just these exact points. And one way that we can do it is for a particular point in the neighborhood. Sergey showed during the treatment of LQR that you can have these particular feedback gains that tell you when you start deviating from the trajectory, how should your action change? And it's going to be changing according to this feedback matrix K that you get as a byproduct of LQG. So there's going to be a linear relationship between the change in state to how your controls should be changing, so that your trajectory is still optimal. For direct collocation methods, we can similarly derive such feedback gains. It's a little bit involved, so I won't go into details during this lecture, but maybe I can discuss it more during questions if you're interested. But in practice, what we end up doing is that we can, when we're training our policies, we can inject noise into the states and then change the corresponding desired outputs according to the optimal feedback gains. And if we do this, if we kind of train with with these changes in the state, we end up the policy that actually always end up converging. So in practice, the joint problem, is very large to solve directly. And we can decompose it into a sequence of trajectory optimization and regression problems, much like you saw on Wednesday, where trajectory optimization is the same, is a collection of independent problems now that you saw before, just now with this additional quadratic term that says basically your controls should stay close to the policy. You could potentially do things that you saw on Wednesday, where you can introduce and keep track of Lagrange multipliers to make sure that this constraint is really a hard constraint. That is, in general, like it would satisfy this constraint exactly, but it comes with a cost. You may sometimes have stability issues if you have Lagrange multipliers, or if you say try to introduce new trajectories or remove trajectories from your data set, you may not, like, if you introduce a new trajectory into your set, what's going to be the Lagrange multiplier there? It's something that accumulates over time, and you may not necessarily know what it should be if you introduce new problems. And the other thing that you would do is you would just end up doing supervised regression, given all of the trajectories that you've optimized. And you just keep alternating between the two. And the nice thing is you can have asynchronous implementations of this. You can have multiple servers kind of running trajectory optimizations, and you can have a neural network training server, so that the full data set never needs to be loaded into memory in any one machine. And so some of the results that you can get if you do this is you can have interactive policies for controlling kind of your simulated characters. For example, this is a bird where the cost is to move to this target, and so I'm interactively now kind of controlling this particular target location. And we see that the policy ends up following this target pretty successfully. Or you can kind of have different characters and kind of different densities, so sort of like four-fin swimming creature. You can also have bipeds that move and follow the target pretty aggressively, and so they're pretty responsive. And you can also have like kind of different types of characters, like if you have something shorter or something very wide, like again how our old walking sofa would end up moving, or quadrupeds as well, and kind of controlling their location, but also their heading if necessary. So that kind of gave you some ideas for how you can do trajectory and policy optimization with collocation methods. So now I can kind of talk a little bit about different applications. For example, how you would deal in the real world with uncertain and unknown dynamics, and also some biomechanics applications that I think kind of are not very obvious, but it's still a very interesting set of problems to look into. So what happens if you, say, do your trajectory optimization for this particular robot, you have some guess at the model for the robot, and try to execute the trajectories in open loop? Well, we've at least did not have luck initially. And so what happened is that we did this trajectory, we have the real robot, and we did trajectory optimization under the simulated model of the robot that was not perfect. We had some uncertainty in there. So for example, we did not know what the individual geometry would look like. So for example, the feet might actually, there might be some small, the height differences between the model and the real robot. We may not know the masses of all the limbs exactly, or like say their centers of mass. And so we were just guessing at them. So one way that you could perform trajectory optimization with this, like you can realize the uncertainty in their models and generate a collection of noisy models by varying these quantities that you're uncertain about, like say perturbing limb masses or centers of mass or locations of contacts. And you optimize over multiple state trajectories over all of these different models. But then you make sure that they share a single trajectory of controls. You can put that as an explicit constraint over all of these different, over all of the different noisy models. And then it's the sequence of controls that you end up executing. At the time, we just executed an open loop on the robot. So what happens, kind of to give you some intuition for what happens, is if you don't have any noise in the models, what we ended up seeing is that the character usually to the robot to get from here to there ends up taking, say, a very large step and kind of has this somewhat risky movement, like rocking heel to toe. But if we optimize width by taking model noise into account, for the same kind of task, we end up getting a more conservative movement that takes like many smaller steps and ends up like not rocking heel to toe. And it is this movement, if we execute it in an open loop, it's much more likely to succeed on the robot. And kind of to show you some other examples of this, these movements. As you can have these turns.
Mm-hmm. Did you try kind of varying the amount of noise? Do you find that like takes more steps the more noise you put in? Or?
Yeah, usually something that we saw is if you increase the noise, it ends up, the best thing to do is not to do anything, and it ends up being like overly conservative. So there's actually kind of this trade-off between how robust versus how conservative you are. And just kind of.
Do you think that if you were able to run this thing sort of, if it was fast enough to run in NPC mode, that you might get even more robust behaviors?
Yeah. So potentially, like, yeah, we necessarily don't necessarily want this overly conservative movement, and to get rid of that is one thing to do is to run things in NPC mode and replan on the fly, and in general to learn models online, which again is similar to what you've talked about in previous lectures. The slight difference here, or like a slightly different treatment that we're going to take, is that we're going to be training policies to output, instead of the controls, actually output the next desired sensory state now. So this, for example, really should be S rather than X, but this next desired sensory state X bar contains, say, what in the at the next time step, what would you expect your join angles to look like? What would you expect your IMU readings to look like? Or say the contact force sensors. What situation would you expect in the future in order to be successful long term? And that's done offline. And at every time step on the robot, you can learn robot dynamics on the fly from past observations, because like you run the robot, you gather sequences of states, controls, future states, you map them, learn this function f. Then you can query a policy. Okay, now in my current state, what should my desired next sensory reading be like? The policy gives you xt plus 1 bar, and then you can use your learned dynamics model to find the torques that would actually make under your learned dynamics model go to the next desired sensory state. So again, it's a pretty similar setup to what Sergey talked about, and this is sort of the nice thing about it is that you're learning this dynamics model online, and Nikhil actually in this very lecture worked with me on this project, and we end up getting like pretty responsive movements when we do this online learning, online model learning. So here, my collaborator at University of Washington is like deviously interacting with this robot and is having way too much fun with this, doing pelvic thrusts. And you can do other things like control the quantities, like the location of the arm. So let's see, how much time do I have? Maybe I'll go on for another 5 minutes and then maybe 10 minutes for questions. In a slightly different set of applications is the motions that you saw. They were pretty sensible sketches of what should be happening, but they weren't necessarily realistic or like biomechanically plausible human movements. So an interesting question to look at is like, what would happen if you actually have very detailed humanoid models? And one of the possible applications for this is if you wanted to like study human movement, you could say for cerebral palsy patients, one of the procedures, or one of the effects is that, well, the children with this condition end up walking in this very crouched gait. And actually one of the effects is that, or one of the reasons for this is that the tendons are overly shortened at around the knees. And an operation that can be done is to try to cut the tendon a little bit and lengthen it, and actually make those kids walk with a straight rather than a crouched gait, which is a lot more energy efficient. But kind of predicting what a human would look like, a particular human would look like, or would walk like after this procedure, it is very uncertain. And like the doctors actually end up like kind of having to do some guesswork as to where they cut and how much they cut. And so one of the ways in which optimization or like trajectory optimization can come into play here is, given a particular operation and like now this new body, what is the optimal way that this new body can walk? And similarly, you can also have it study the effects of, say, various equipment like prosthesis or say various backpacks or things like that, and what effect they would have on the gait. So you can perform these virtual experiments without ever having to do them in the real world, if you trust your models, and if you trust your trajectory optimizer to be smart. So something that you can do is augment your existing models with musculotendon actuators, and then measure the effort using metabolic energy expenditure. And I think I probably would skip the details of this in the interest of time, unless like we really do want to go into the details of musculotendon units and their models. All right. Yeah, I think in general, basically the entire musculotendon units, when people talk about it, it consists of a contracting muscle fiber that's connected to the character's body via the tendon. And this musculotendon unit, the MTU, has a total length, but within it, the length of this muscle fiber actually can vary, and it has a pretty large effect on the amount of force that the muscle can generate. And when the muscle fiber does contract, it exerts the force that's transmitted through the tendon onto the character's body, which results in a torque that is applied to the joint, and different configurations actually have, but under different body configurations, you can actually have the same force generating different torques. And the total force is generated is a somewhat complex function of the fiber lengths and actually like how they're changing. This I really don't want to go into the detail of, but in general, roughly, when the fiber is overly when the muscle fiber is overly contracted or overly stretched, the muscle is actually not as good at generating force. And you can have the muscle activation level, which is something that is being sent from your brain, like how much do I want this muscle to be contracting right now? And there's some additional involuntary passive force acting on the muscles that basically pulls the muscle back when it's stretched too far. And you can model the usage now with metabolic energy expenditure, which is kind of a more biologically plausible model of effort than, say, squared sum of torques, for example. And there's sort of, in the literature, people have identified, like, usually there's a lot of muscles in the body, but especially for the lower body, people in biomechanics kind of have grouped them into this representative, reasonably small set of muscles. And so those are going to be the actuators that we're going to be working with now. And we can apply the same trajectory optimization methods to kind of get the results where you can now actually, the muscle fiber lengths are additional variables in our optimization. So we're planning how much should the fibers within an individual muscle should be stretching or contracting. And you can also get their activation levels. And we end up observing, actually, that it ends up matching both the torques and the joint angles match reasonably close to what human subjects end up doing on a treadmill for walking. And similarly, you can try to get running movements as well. So this is basically, if you command a higher movement speed, you're going to get something like running. You can also try to do like low gravity running just for fun, or kind of gait initiation, and observe other quantities that actually end up agreeing with what humans do, like center of pressure for the feet, gait termination, various jumping movements, or various kind of biomechanically plausible kicking movements emerging from scratch. And there's some other interesting work to kind of motivate this a little bit more. People have also done it for control policies as well, not just in the context of trajectory optimization. Took these muscle-based models and make them. Let's see, can I? Oh, I guess I can't control the video here. Well, that's a pity. So yeah, to get these biomechanically plausible policies. And one thing I just want to highlight is that like that work kind of had a lot of special casing and a lot of hand-designed architectures. But we saw, for example, like you'll see later in the course, say results for trust region policy optimization for walking. And it's amazing that we're able to find these solutions. Like trust region policy optimization is a great algorithm, but the solutions that it finds are not necessarily, say, what you would call biologically plausible. And I think it's a very interesting question, is like, what would happen if you were to augment these kinds of models with more biologically plausible actuators, or something that does act like muscles, and then run TRPO on it. I think that would be an interesting thing to look at. So yeah, I think that's all I wanted to talk about. So thanks for listening, and if you have any questions, I'd be happy to take them now. Hopefully that was all reasonably clear.
Any questions for you?
Yeah.
When you were showing the, you were generating some trajectories and then fitting neural network trajectory policy with that, you were still saying that you're running that open loop. But if you feed that trajectory, can you just like check what's the state and then apply the control that is output by this policy, or do you call this open loop?
You're not, like, this was not doing, so it depends on which result you were talking about. Do you mean these results? So I should say, like, these are kind of results from two slightly different papers.
Before that.
or these?
Before the Darwin.
These ones, you mean?
Yeah, before when you, yeah, all these, yeah, yeah, here, all these.
Okay. So what about, this is running a policy that is outputting either the controls or the desired next state.
And it takes in the current state. And
Yes. Yes. Yeah. This is not a trajectory that's running an open loop. This is like again, that green cursor is me moving it interactively.
So I don't know why I thought you said at some point that you were running these open, or maybe it was for the Darwin.
It was for this particular result for the Darwin. Like if you run these trajectories, you just try to optimize a trajectory in simulation and try to run it in an open loop on the physical robot. Then end up like not working.
So this was not using the technique that you described just before of like feeding a policy to all the trajectories?
Yeah, this was not. These particular results, you were just optimize. This is just one trajectory that was optimized, and you try to execute it.
I thought it was another example of the work.
So this example, yeah, this is running policies now.
Okay, good.
You can tell because it's a different color, right?
Yes, yeah. The white Darwin runs policies, and the black Darwin runs trajectories. Oh, I don't know. It's not playing. Yeah. So this is running. This is running now a policy, and that takes current sensors into account. Good question.
So have you or anyone else tried to do some kind of policy learning stuff with the muscle models?
No, I think it would be really interesting to look at, but yeah, people haven't really looked at that recently. I think it'd be a cool project.
Yeah, it might be interesting, for example, to see to what degree things like trip reactions can kind of emerge naturally.
Yeah.
As a consequence of some particular kind of control strategy.
Yeah, exactly. So, because I think basically one nice thing about muscle models, or something that acts like it doesn't necessarily need to be these very detailed, having the precise numbers of what we think muscles in humans behave like. But I think one interesting consequence of them is that they're actually controlled. You can potentially control them as binary spikes. And so your decision variables, right now, we're typically applying continuous torques. With muscles, you can just send them like contraction spikes every once in a while. So now your control signal is going to be binary, and that'll still result in smooth and sensible movement. So it may be a very different search space for your policies, which actually might work better. Maybe not. So that's...
Could you say a few words about some of the systems questions in regard to the policy learning work with the flying characters?
Mm-hmm.
You had some kind of parallelism stuff going on there.
Yeah.
Things like that.
Yeah. So as we saw before, like if you were to try to run this algorithm on multiple machines, you may have, like, if you have k machines, you can have a particular node be responsible for a subset of trajectories, and continually optimizing solutions to these trajectories, and then sending the solutions to the neural network training server of the network. At the same time, the neural network training server sends the most recent set of parameters to each of these individual nodes, and they try to stay close to the resulting policy. And so that's kind of one of the these kinds of asynchronous updates. When we tried it with Lagrange multiplier methods, we didn't try didn't spend a huge amount of time on it, but this asynchrony ended up messing things up when you're also keeping track of the Lagrange multipliers. And the additional thing that can also happen is that you can have this, play this in a curriculum learning setting where this set you may at some point later add a new machine and a whole new set of trajectories, which you can do here. You can add or remove trajectories. And not having to keep track of Lagrange multipliers kind of allows you the freedom to do that. But it does come at a cost of potentially not matching the solution, or like not matching that constraint exactly.
Well, I guess that's it for today's lecture. The office hours today will be actually across the street in Satar Shadai on the 7th floor in the open lounge area on the west end of the building. So if you have questions about the homework and things like that, that will be the time to go to those office hours. And then we'll resume our regular lectures on Wednesday with John Schulman. See you all then.